Hi, this is John from caveofprogramming.com. In this tutorial we're going to take a look at blurring the screen in our particle explosion program. So if we run this at the moment, we've got an explosion and it's circular, and it should happen at a similar speed on any computer, although on a slower computer it's going to be jerky. And in this tutorial we're going to look at adding a blur effect, which will make it look a lot nicer and a lot more like some kind of weird natural phenomenon than it does at the moment. If you are finding that this program is already jerky on your computer, one thing to do is make sure that you compile the release target. So in Eclipse, that's project build configuration set active release, because the release versions of programs which are not set up to use the Eclipse debugger or Visual C++ debugger, which we're not using anyway, we haven't used it, they run faster than debug programs. If you've got a really old slow computer, then you might get very jerky results with this very expensive blur algorithm, expensive in terms of CPU time, but let's have a go at it anyway and see how it looks. So I'm going to go to my main.cpp, and in main.cpp we're actually at one point clearing the screen, and I'm not going to clear the screen anymore. I'm going to get rid of this. What we're going to do is blur the particles out. Every time this loop iterates, we're going to apply a blur, so a particle will leave a blurred trace behind it. And at the moment now, if I run this, we're just going to see all the positions of all the particles as they go along are not going to be erased, so it looks quite horrendous, but it's going to look good when we apply the blur. So I'm going to implement a method which we're going to call before updating the screen, before displaying the results of plotting the particles, which I'll call screen.blur. Let's call it box blur. There are various ways of blurring the screen, doing blur algorithms, also on photographs for that matter, in photo editing software. You can use a Gaussian blur, which is a kind of natural looking blur, but we're going to use a thing called a box blur, which is very simple to implement. And this is going to be the most difficult bit in some ways of the whole tutorial. So it's going to take a while to explain this, but it will give us a really beautiful effect, at least if your computer is fast enough to display it reasonably quickly. Box blur, there are various ways of implementing it, and I'm going to just implement it in a kind of common sense sort of way. I'm going to explain what we want to achieve, and we're going to just code that. But if you, after seeing this video, if you Google on the internet, you can find various ways of optimizing box blur to make it run faster. So if you do experience speed issues with this blurring algorithm, there are ways of optimizing it and making it faster, and you can find that by searching on Google quite easily. There's a number of pages that explain that. Let's go to screen.h and add this, the prototype for box blur, as a public function here, and public method. Go to screen.cpp, and somewhere in here, let's go ahead and implement this. Let's say void screen box blur. Now what I want to do here is, instead of drawing screen directly, I want to look at the screen as it is with the pixels on it, and then calculate a new screen with blurred values for all the pixels. So I can't apply this algorithm to the screen pixel by pixel, because we'd end up confusing the value calculated for one pixel with the values calculated for the last pixel. We can't mix up our workings as we're going along. What we need to do is create a whole new screen of pixels and put our calculations in this second screen, and then draw that second screen. So in screen.h we've got a buffer somewhere here. So we've got this buffer, and I'm going to create a second buffer so that we can look at one buffer and put our calculated blur results in the second buffer. So let's copy this line, and I'm going to call this buffer 1 now and buffer 2. So now we need to go to screen.cpp and look at the syntax errors now, and wherever we've got buffer m_buffer, we need to have buffer 1 and buffer 2. So here I've got buffer 1, and we also need to initialize m_buffer 2, null. And scrolling down here, this is where we're actually allocating the buffer. So I'm going to copy that line, and we're going to allocate buffer 1 and buffer 2. Here we're clearing the buffer, getting rid of any garbage in the memory there. So now we want to do that with buffer 1 and buffer 2. This is the screen clear function, which we're actually not going to use, but just for the sake of completeness, let's add buffer 1 and buffer 2. Since we're not going to use this function, and since I'm not sure anymore exactly what it should probably do, we're probably better off just getting rid of this. Let's get rid of the screen clear function, because I'm no longer sure what bit you would want to clear or why in this program. So let's clear it. Let's get rid of it. Continuing in screen.cpp, this is where we're in set pixel. This is where we're plotting pixels. So I don't want to plot the pixels to the second buffer, only to buffer 1. So I'm going to just change this to buffer 1. And similarly, when we update the texture with the results of the pixels in the buffer, I'm going to just use buffer 1 there. And finally, we need to remember to delete the buffers. So let's delete buffer 1 and delete buffer 2. Now, if we go back to the box blur implementation, so I want to copy from one buffer and write to another, and the buffer that I want to write to is buffer 1, because it's buffer 1 that we're then going on to draw on the screen. But at the moment, all the pixels are stored in buffer 1. What I'm going to do is I'm going to swap the pointers. So buffer 2 points at where buffer 1 originally pointed at, and then we're going to copy from buffer 2 into buffer 1. Now, a naive way of doing that would be to say m_buffer 1 equals m_buffer 2. Let's put a comment here. Swap the buffers. So pixel info is in buffer 2, and we are drawing to m_buffer 1. So a naive way of swapping this would say m_buffer 1 equals m_buffer 2, and m_buffer 2 equals m_buffer 1. The object here is to point buffer 2 at whatever memory buffer 1 was pointing at, and to point buffer 2 at whatever memory buffer 1 was pointing at. Have I said that the right way round? Well, hopefully you understand what I mean. But the problem is this isn't going to work, because we've redirected buffer 1 to point at buffer 2, and then we're setting buffer 2 to point at the redirected buffer 1. So these now both point at the memory that's pointed at by buffer 2. What we need to do is have a temporary variable in here. So these buffers are of type uint pointer, uint32 pointer. I need a variable called temp here. So that's a pointer, and I'm going to say temp equals m_buffer 1. So we've stored the location that buffer 1 was pointing at. Then I'm going to change buffer 1 to point at the buffer 2 memory. Then I can change buffer 2 to point at the stored original value of buffer 1, which is now in temp. This is a very common little design pattern in computer programs, where you use a temporary variable and use it to swap two values. In fact, I think we've even seen it before in this course when we were reversing a string. We've seen a similar, we've seen a similar idea, although I can't quite remember. So let's just check this. We've got temp at buffer 1. Buffer 1 is then pointing at buffer 2. Buffer 2 points at temp, so we've swapped the areas of memory around. Now what we want to do is iterate through all the pixels, look at buffer 2, which now contains the pixel information that's been written into it, and do some calculations to create the blur effect and copy it into buffer 1, which is now a clean buffer. And then we can plot those values on the screen. And we're not going to erase any of the buffers in between iterations of the game loop here. What we're going to do is we're going to keep blurring the same screen more and more. So when we draw a screen, we'll blur whatever was on the screen previously, and then we'll take whatever's on the screen previously, draw the new pixel on it, and then blur it. So every time we redraw the screen, the stuff that was on it previously will get more and more blurred. Only the new stuff will be comparatively sharp, and that's going to give us some beautiful trails on our pixels that will blur out more and more as the pixel moves along, a bit like a sort of comet trailing its sort of fiery tail that sort of expands as the comet goes by, or I imagine it does. So now let's iterate over all the pixels. So let's have a loop here for int y equals 0, y less than screen height, y plus plus. And within that, we're going to go over all the pixels in this particular row. So for int x equals 0, x less than screen width, x plus plus. And by the way, I was thinking of implementing a getPixel function, but the trouble is we've got this problem that we have to get the pixel from one buffer and sort of write into a second buffer. So it's not like we're getting and setting pixels on the same buffer. So I'm just going to implement the getPixel stuff using the bit shifting stuff that we've seen previously in this function here, directly in here, to get the colors of pixels from what is now buffer 2, and then write them using setPixel into buffer 1. Now within this, we've got a particular. This identifies a particular pixel. So we've got a particular pixel, but surrounding that pixels are 8 other pixels. So you can think of them as, let's use zeros. They look a bit like this. So we're looking at this pixel in the middle here, but around it are a bunch of other pixels, and what we want to do is we want to add up the color values, the red, green and blue values in each of these pixels. That's a total of 9 pixels. Then divide the results by 9 and plot that result back into the pixel we're interested in setting here. So the color values of this central pixel, which is at location xy, will become an average of the color values of all of the pixels around it, including itself, and that's what creates the box blur effect. So to iterate through all these 9 pixels, we're going to have yet another nested loop in here. We're going to say for int col, or I could use a short or something, but I use int because we've got enough memory here. For int, let's say row. For int row equals -1, row less than. So we'll do this loop while the row is less than +1, row plus plus, and we're going to add this value which ranges from -1 through 0 up to +1. We're going to add that to our x and y, actually to the y position for the row, and that will give us this row for -1, this row for 0, and this row for +1. And within that we'll have another nested loop for int col equals -1, while col is less than 1. Sorry, I should have said that less than or equal to 1, because we want this to go -1, 0, 1. While col is less than or equal to 1, col plus plus. And now we can calculate the coordinates of each of these pixels in this grid. Let's call this int, we can call it like pixel x, or new x or current x or something. Let's call it current x equals x plus col, and int current y equals y plus row. So if you think about it, what we'll end up with here we'll end up with, for every pixel that we look at, every single pixel on the screen, we'll end up we'll end up iterating through all of the pixels in this grid of 9 pixels that surround it, including the actual pixel itself, for when row and col are both 0. So this current x is going to range over all of these pixels one by one, if you think about it. Now we want to get the colour values from these pixels and add them all together. So I'm going to have outside of this inner loop that iterates over the grid of pixels here, but within these outer loops that iterate through each of the pixels on the screen, I need to have some colour values that I can total up, and these colour values are going to end up being more than you could store in an unsigned char, because we're adding up the values from 9 pixels. So I'm going to have here an int, let's call it red total, and I'll set it equal to 0. Int green total equals 0, and int blue total equals 0. Now we need to get the colour of the pixel at this location and add up all the separate components. But because we're iterating over all the pixels in the screen, it's possible that this pixel could be off the edge of the screen, because if we start with pixel x equals 0, y equals 0, then we try to get a pixel that's to the, let's say, to the upper left of it, for example, that pixel's not on the screen. So we need some way of ignoring pixels here that are off the edge of the screen. So let's say here, if current x is greater than or equal to 0, and, so we want a logical and, which in C++ you use 2 and signs, and also we need to say that the current x must be less than the screen width, because the maximum x we can have is 1 less than the screen width, because we start numbering at 0 and we've got screen width number of pixels. This is an array. So we need to make sure that x is between these 2 values, and also we must have current y is greater than or equal to 0, and as well current y must be less than screen height, and if so, we can go ahead and get the colour value of that pixel. And by the way, in C++, the way these ands function, or ors for example, is the computer will go through each of these clauses, and for ands, for example, all of these must be true to make the condition as a whole true and to execute the if. They have to all be true because we've anded them all together. And so if it goes through, it'll start checking them from the left, and as soon as it finds one that's false, it will stop going through all of these, and it won't bother doing the rest because there's just no need. As soon as you find a false one, it's going to check all of these, and it's only going to do the if every one of these conditions in here that we've anded together are true. That's because we've used the logical and. Let's get the pixel colour there. So I'm going to say I'll use the SDL type uint32, which means an unsigned integer that is guaranteed to be 32 bits. Normally it is 32 bits, but it's not guaranteed. It could be different on your machine. It's possible. So uint32 colour equals, and now we need to access the buffer that contains the pixel information, which is now buffer 2, because we swapped it with buffer 1. So we need to say buffer m underscore buffer 2, and the formula is it's y, sorry, not y, but current y times screen width that's the number of rows down that we're going, plus current x. This is how we get from x and y coordinates to an index within this array, which again, you have to think about it a little bit the first time you see it, but then you see that this does work. So that gets us the colour, and now we need to get the red, green and blue components out of that colour so that we can sum them all together. It wouldn't be any good just summing up all the colours and then dividing by 9 to get the average colour, because, well, if you just think about it carefully, you realise that it wouldn't work. It takes a bit of thinking about, but in fact that just doesn't do the trick at all. We need to actually go to the trouble of getting out the individual red, green and blue components, summing them separately and dividing them by 9 separately. So let's take a look at screen.h. No, not screen.h. Let's take a look at setPixel actually, because in there we see how the colour information maps to an integer. We see that we've added red here and then shifted red a byte along to the left, and then green and then blue. So the way it works is we've got a alpha value, I think, because the blue is also shifted right at the end there. So I think the format here is we've got red here, green, blue, and then alpha, which is a transparency that we're not using. So the red, if I've got this right, is shifted 3 bytes along to the left in this thing here. So we start off putting it right there, and then by the time we finish, we've done 1, 2, 3 shifts, which is 24 bits, 3 bytes to move it 3 bytes over, to the right hand side there. Let's see if I can just redo my typing there. There we go. So to get the red value out, what we can do is, let's go back to the box blur. We can say here, again, we'll use the SDL type uint8, which is an 8-bit unsigned 8-bit int, or we could use unsigned char, it's the same. Red equals colour, and we need to right shift the colour by 24 bits to get the red value, if I've got this right. And this is tricky to get right. Every time I implement it, I do something wrong and then have to think very carefully over what I've done, putting in cout statements to check that all the different values are what they expect, or what I expect them to be. But I'm hoping that I can get it right this time. So now to get the uint8 green value, that was only shifted by 16 bits in the colour, and uint8 blue is just shifted by 8 bits, and the last value in the colour is the red value. So I just shifted 8. After I put the blue on, I only shifted it by 1 byte, 8 bits to the left. So if we shift the colour by 8 bits this way and then take the last 2 digits of it, in effect, in hexadecimal, we've got the blue value, as we saw in a previous tutorial. Now we can say here, if we get a valid pixel and we can get colour values out of it, we're going to say red total plus equals red, green total plus equals green, blue total plus equals blue. Now we've summed up all these values for a box surrounding this pixel here at x and y, and we're going to go after this loop that iterates over that grid of 9 pixels, and now we can say uint8, this is going to be the actual colour that we'll set the pixel to, red equals red total, divide by 9, because there are 9 pixels in that grid. uint8 green equals green total, divide by 9. uint8 blue equals blue total, divide by 9. We've used red up here, but there's no problem using it here as well, because remember, variables are scoped to the innermost pair of brackets where they're defined. So these colours, they only exist between these 2 brackets here, these variables. then we use them, and then we discard them basically. Similarly, these totals here, they're scoped to these brackets that actually define the business of checking one pixel. I think it should be there, if I've got that right. Yeah, so that they're defined to the innermost set of brackets belonging to the for loops that actually check one individual pixel, and then for the next pixel these are redeclared, so they're completely reset. Okay, so now we've got that, we can use our set pixel, which remember sets into buffer 1, but we copied the last lot of pixel information on the screen to buffer 2. We're reading from that, then plotting back into buffer 1 with set pixel, which will plot the results of the blur on the screen. And next time we go round the game loop in main.cpp, we'll blur that same buffer again after plotting the new pixel on it. So it'll get more and more blurred as it goes along for any given particular pixel trail, which is what we want. So let's say set pixel X, Y, red, green, blue. Now if I've got this right, it will work, and if I haven't, it won't. Let's try this. Let's run it. I don't know if I've forgotten anything here. So yes, it works. Now this doesn't look too great at the moment. When it expands a bit like this, it starts to look kind of cool, especially if you look at the pixels on the outer edge. The reason it doesn't look as good as it does in the final program is because we still need to tweak the behaviour of the pixels. We've got a big sort of solid white bunch of pixels there, a big load of solid colour, and we want to do some things like making them move in a more interesting way and trying to make this circle more ragged as well, which we can also do. So we're going to look at that in future tutorials, but I'll leave it there for now. So again, I'd encourage you to have a go at that. If you really get stuck and you can't get it to work, you can always copy my source code here and try to examine what you've got different to my code. I'll make this code available wherever the lecture's available on my website. On YouTube I can't attach the source code, but it'll be on my website. If you're watching on udemy.com, it'll be attached to the lecture. If there's some other system I have this video on that only allows you to attach source code at the end of all the lectures, then I'll attach it to the final lecture, but it will be there somewhere, except on YouTube where you can't attach files. But this is very tricky, but if you can get your head around this, or even 90% of this, and if you can get it working more to the point, then you've really done something quite amazing. It took me a long time before I could get the hang of blur algorithms like this. This is pretty advanced C++ really. You have to think hard to get this to work. So it's a challenge, but it's a challenge worth having a go at. So we'll look at probably changing the pixel motion a bit more in the next tutorial, but we've almost come to the end of this now. We've almost got our final program. So until next time, happy coding.